So we're going to continue 8.3, confidence intervals for means. And we're going to do that by talking about the GOAT. Many people think that Michael Jordan is the greatest basketball player of all time. Do you guys agree, or do you think it's someone else? Okay. All right, well, let's see. Michael Jordan has a career scoring average of 30.1 points per game. Michael Jordan has a career scoring average of 30.1 points per game. Some curious statistics students wondered about his scoring average for his home games. They decided to take a random sample of 15 home games from Michael Jordan's career. Here is the number of points he scored in each of these games. We are going to construct and interpret a 95% confidence interval for mu, the mean number of points that Michael Jordan scored in all of his home games. So, what does this need us to do? A state plan do conclude. All right? Now, listen very carefully. That's how you feel right now. You should be a little suspicious because you were given the individual data. And the sample size is only 15. Why should you be suspicious? You're probably going to have to graph this. It's going to be great. So we'll get to that in a minute. But for now, we're just going to state what we're about to do. State. What are we going to do? Anyone know the third word? Estimate. We will estimate. We are estimating an interval, y'all. So we will estimate the true mean mu, number of points that Jordan scored in all his home games at 95% confidence level. All right. There's our intro. Yeah. We are going to estimate the true mean mu, number of points that Jordan scored in all of his home games at 95% confidence level. We know that it's 30.1 in all of his games, but we need to see what it is in his home game. So we have taken a sample of 15 of his home games, and that's what we're about to find out. All right, now we're going to plan. Random. Do we have a random sample? Yes. It says so. We have an SRS of 15 of Jordan's home games. Yeah. So far, so good. Independent. How do we check that independent condition? We do that 10% thing, right? So we need to make sure that 10 times the sample size is less than the population. All right, so 10 times 15. What's 10 times 15? 150. Do you think that the population of Jordan's home games is bigger than 150? We might need to bring in an expert. Hudson, how many home games are there approximately in an NBA season?
Less than 150.
Less than 150, okay. But Jordan played a long time. So this would be like all of his home games. Do you think he played more than 150 home games in his whole career? Probably. So we're probably good. Do you guys have any questions so far? All right. It's time for the fun. Let it begin.
It's 73.
It's 73 home games? Well, there you go. So he only had to play 2 seasons to basically get there. 2.5 seasons.
No, 73 total.
Oh, 73 total games.
41 home games.
So 41 home games. Okay. So did Jordan play more than, what? 4, 8, 12, 16. Did Jordan play more than 4 seasons?
Played 73 home games total.
Okay.
Like every
So,
What?
Wait, I found 536.
Yeah, 536 home games. I don't know what you're talking about, kid.
home games 73.
Not ever. No way.
82 games in a season, like half one.
Look, it's fine, okay? Can we move on now? All right. No, we're not ready to do yet. What do we need to do next? We got to check the normal condition. Ladies and gentlemen, do we know what the shape is of the population of his home games? We don't know. Do we have a sample size that's bigger than 30 so the central limit theorem applies?
Yes.
We don't. So, what do we get to do? We're going to graph it. Hey guys, I'm going to show you guys how to use your calculator to do this and save yourself some time in the future on the do part. So, if you guys will, please go to your calculator. Now, we have individual data. And we need our calculator to graph it for us. So what do you think we should do? We should probably put the data in our calculator. So please go to Stat Edit. Everybody go to Stat Edit. And we need to input this data into our calculator under L1. Stat Edit L1. Put the data in. So now we have our data in. Here's what we need to do, you guys. We need to look at the box plot. Now you can make a dot plot if you want, but the calculator will do the box plot for you, so you might as well do that. Do you guys remember how to make a box plot in your calculator? You need to go to second y equals. Everybody go to second y equals. Does this look familiar? You need to go to plot 1, so hit enter on plot 1. Make sure it's turned on. Then you'll go down to type, and you want to select the box plot that has the outliers. So you have to go to the right and select the box plot that has the outliers showing. It's the 5th graph. Make sure you select the box plot with the outliers. L1 is your list. I'm sorry, it is the 4th one. I'm sorry, it's the 4th one. It's the 4th one.
Fourth what?
The 4th graph. It's the 4th type.
I already wrote
It's the 4th. It's the 4th. I know I'm a liar. I'm sorry. All right. X list is L1 because that's where your list is. And then you hit graph. If you don't see the graph, then you hit zoom 9, and that will show you your box plot. Now, where are these numbers at, right? So if you hit trace, it will give you the numbers, right? So what is the minimum? 24. What is Q1?
27.
27. What is the median? What is the Q3? What is the maximum? By the way, you guys, if I were to write those 5 numbers down, what would I be giving you? The 5-number summary. Might be important to know that. Yes, ma'am.
How'd you get it to do
I hit trace. Those are the 5 numbers for the 5 number summary. Hey, does anyone remember how to calculate IQR?
Ooh,
Yeah.
1.0. It's Q3 minus Q1.
Q3 minus Q1. I could use this to get Q3 minus Q1, which would be the IQR. Does anyone remember how to test for an outlier? 1.5 IQR. Now, here's the cool thing. If there was an outlier, because I selected the box plot with outlier type, it would show me the outlier. So I don't even have to calculate it if I use my calculator.
Why didn't we do this at the beginning?
Why didn't we do this at the beginning of the year? Because you were not old enough and wise enough yet. Now you are. Welcome to the world. All right, cool. So here's what we're looking for, guys. Do we have any outliers in our data? Do we have any strong skewness? Does our sample data look approximately normal? Then guess what? It probably came from a population that was approximately normal, and therefore we can assume that the normal condition has been met. So now we can go back to our state plan do conclude. And now we're under normal. And we say, since the population, this is under normal, since the population shape, yes, this is under plan, since the population shape is unknown, and n is less than 30, the sample graph is used, and guess what? We get to sketch the sample graph. So you're going to sketch your box plot. Can someone remind me what Q1 was? 27. And the median was 31? Is that correct?
Yeah.
And Q3 was 35? Okay. All right, so here's our box plot. This is a pretty nice looking box plot, but oh no, I have forgotten a very important thing on my box plot graph. What is missing on my box plot graph that is extremely important? I did not label my axis. Oh man. Points per game for 15 home games. All right, cool. Now, I have my box plot, I have my graph, and I'm going to notate that there are no outliers, no strong skewness. There's actually no skewness at all, but there's no strong skewness. So, the T procedures apply. The T procedures apply. Ladies and gentlemen, that is how you need to do the normal step if you have to graph the data. You notate that the population shape is unknown, that n is less than 30, so your sample graph is used. You show the sample graph, notate that there was no outliers, no strong skewness, and that the T procedures will apply. That way you can now use those T procedures to do the do. Before we do that, do you guys have any questions about this step? Everybody good? All right. let's do the do. Back to the calculator. Back to our calculator. Now, guys, here's the great news. The data is already in the calculator. So we're just ready to go. Stat, test. Do you guys remember which one we're using? T interval. This is number 8. T interval number 8. Now, for this problem, did we have data or did we have stats? We have data. It's already in L1. And so we just need to confirm. What is our confidence level? We are making a 95% confidence level. So I can just go right down here to calculate and hit enter. Give your calculator a second. It does take a minute. And there's your interval. Not only is that your interval, but it also went ahead, it also went ahead and showed you the X bar for the sample, the mean of the sample, and it gives you the standard deviation of the sample. I'm sorry that it's not showing on my screen, but you should already have it on yours. So now we go back to our state plan do conclude, and now we're on the do part, and we use a 1 mean T interval. That's the name of this specific procedure. And you can just write down what your interval was. What was the lower boundary of the interval? 28.204. What was the upper boundary of the interval? 32.863. Okay. Now, because we were not already given this information in the problem, I am going to go ahead and write down the mean and the standard deviation that was given to me by my calculator. What was the mean of the sample of all of his home games? 30 point what?
30.5.
All right. And what was the standard deviation of all of his 15 home games?
4.207. Or 4.21.
Okay. All right. So, just to continue to analyze this data, all of his games, he had a career scoring average of 30.1. Based on the average of these 15 randomly selected home games, did he score a little better at home or a little worse at home? Looks like he scored a little bit better at home. And this is our 95% confidence interval for what the true value of his home game scoring could be. So it's not that much different than his overall scoring for his entire career, no matter where he was. But this is his home game scoring interval. All right, what's left? Just got to conclude now. We are, what are we? 95% confident that the interval from 28.204 to 32.863. What does it do? What does that interval do? Captures the true mean mu number of points per home game for Jordan. Now, let's say Michael Jordan's having a press conference and someone's asking him, "Hey Jordan, when you were playing, man, did you just totally go crazy at home games and just score 35 points per game?" And he's like, "Yeah, man, I sure did." What would we think? That would be that he's maybe over-exaggerating and maybe misremembering how things were back then, okay? Now, if he's like, "Oh, yeah, I scored like 32 points per game when I played at home," we would probably believe him because that's within our interval, Okay? Anything that's within your interval is believable for 95% confident that it would be believable. Cool? There you go, guys. There is a full state plan do conclude when you have to make a graph. Wasn't that fun? You want to do it again? No. Oh, come on. All right, fine. We won't do that again. At least not today. So, do you guys remember I think it was on, I guess it was Monday, maybe? Yeah, Monday. I told you guys how sometimes you want to know the percent confidence you're going to be. You know what margin of error you want. And so you have to solve by algebra to find the sample size. Well, we have to do that for means as well. So, here's how this one works. Desired margin of error has to be greater than or equal to the z-star critical value times the standard deviation of the population divided by the square root of the sample size. Now, there's some things here that you might be questioning. First of all, Miss Lakey, why did you tell me that I need to use a t-star for means and now you're throwing a z-star up in here? Here's why. Do you guys remember when we were doing t-star critical values yesterday and we went to inverse t? When we went to inverse t, it asked us for two things. It asked us for area and it asked us for what? Degrees of freedom. And how do you get degrees of freedom? You take the sample size minus 1. But ladies and gentlemen, this is me trying to figure out how big of a sample size to take. So is there any way to get degrees of freedom if I have not taken the sample size yet? No. So I can't use inverse t whenever I am trying to figure out how big the sample should be. But do you remember when we were increasing the sample size, how t-star was getting really close to z-star as my sample size got bigger? So z-star is a good enough estimate for what t-star would probably be. So we're just going to go ahead and use that z-star for this part of the problem, okay? Also, this does not say S sub x. What does S sub x stand for? Standard deviation of the sample. If we have not taken the sample yet, because we're trying to figure out how big the sample is going to be, how are we supposed to use the standard deviation of the sample? Well, we can't. So we will have to be given a standard deviation from a previous study or a pilot study. Okay? So that's how this is going to work. All right? So it's a little wonky. Lots of estimation, but at least gives us a sample size to go for, okay? So here's a problem. Taste the rainbow. A group of students would like to estimate the average number of pieces of candy that come in fun-sized packs of Skittles. They would like their estimate to be within 1 piece of the true mean, mu, at a 98% confidence level. A Google search reveals that the standard deviation of the number of Skittles in a fun-size pack is about 2.4 pieces. Again, standard deviation has to be given to you from somewhere because you need it to do this formula. What is the minimum number of fun-size packs the student should randomly select to get a satisfactory estimate? So here we go. We're going to do desired margin of error has to be greater than or equal to the z-star critical value, again, only because I can't use t-star here, times the population standard deviation, only because I can't use S sub x because I haven't taken the sample yet, divided by the sample size, which I'm going to solve for. All right, I'm going to kind of write down everything we know. What is the desired margin of error? 1. What is the z-star critical value for 98%? Chances are you don't remember that one. So, we're going to have to remember how to find it. If I have 98% in the middle, that means that there is 1% on either side. That means I have an area of 0.01. And since we're looking for a z-star critical value to use, we can use inverse norm. The area is 0.01. The mean would be 0. The standard deviation would be 1. This is how you get the z-star critical value for any percent, but that's your 98% z-star critical value. And you're going to use the positive version of the number. So what z-star critical value am I going to use? 2.33. That is the z-star critical value for 98%. If you ever just want to memorize it, feel free. And then the standard deviation that was Googled and found was 2.4. All right, guys. So now we're just going to plug all this in. 1 has to be greater than or equal to 2.33 times 2.4 over the square root of n. Now, my algebra gurus, this is going to be solved slightly different than the one for proportions because the square root sign is only on the bottom of the fraction, not the whole thing. So the steps are going to be slightly different. But what is still the same first step? I'm going to divide by the z-star critical value. That is still the first step. So 1 divided by 2.33. And remember, we don't want to round until we get to the end. So 1 divided by 2.33 is 0.4291845494. That has to be greater than or equal to 2.4 divided by the square root of n. Now, our next step, again, is going to be different than it was for proportions. What would be the next step that we would need to do? Very good. I need to multiply by the square root of n. I'm going to multiply by the square root of n on both sides. Okay, so here's what we have. We have 0.4291845494 square root of n is greater than or equal to 2.4. Yes?
Didn't you multiply by 2.4?
Nope. Because that does not clear the fraction. Okay? And now what do we do? I don't multiply by the decimal. There you go. I'm going to divide by that super long decimal. Now, remember the other day I told you guys there was this cool little trick. It still works here. So, here's this step. The square root of n has to be greater than or equal to the 2.4 divided by that big long decimal. So notice, guys, all we did is we're switching the square root of n, which is on the bottom of the fraction, with the big long decimal. That's basically what we've done here, okay? We're just switching what's on the bottom of the fraction with the other side of the equation. So 2.4 divided by blah, 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 is 5.592. And what is the final step?
Square.
I need to square both sides. Now, what does your sample size have to be bigger than?
31.27.
31.27. So, how many fun pack size of Skittles do we need to look at?
32.
At least 32. Very good. What questions do you guys have about that? Super exciting, isn't it? So fun.